Hey, okay, so it is, God, I'm looking a little tired there, aren't I? That's all right. Hey, it's week 9, and we're gonna do a little 214. I've got Dustin in the room, and I started looking at the problem a little bit, and it looked like there was a little bit of information missing, but I think it's all there right now, just in terms of the pipe diameter and all that. And I think what you guys are gonna find is that this problem, again, is going to come down to friction losses, which you can treat as an efficiency, more or less. I think one thing you've probably taken away from the course thus far is, you've got power in, you've got power coming out, and somewhere in between, you're losing it, and you're losing it to joule heating in your electric lines. You could be losing it to friction in a belt. You could be losing it to electromagnetic leakage in a motor. You could be losing it to friction here in the case of water. So in every one of these cases, you still want to keep the first law of thermodynamics in mind. Power out is always going to equal power in, but then you got to account for the leakages. And the same thing, in a lot of ways, is true of money, because you can just think of these little taxes and interest rates along the way too, either making you lose money, or if you're the bank, somehow bringing more money in. So eventually, the energy and the two money models should mesh somewhere. So let's just take a look at the week 9 stuff. Down in there. Learning Unit 9. And I do remember a couple weeks ago, we looked at the energy value. So we just used the ideal gas law, PV equals nRT, to see how much energy is in compressed air. I know we spent a lot of time last week looking at the energy required to pump water. And this should be all pretty straightforward right now. Kilowatt hours and BTUs, not a big deal there. Yeah, so this one's a little trickier in that you're not just putting energy into the air by compressing it. You're actually getting a little more energy by burning natural gas. Okay, so let's look at heat rate for a second.
You want to jump into problem 2?
Yeah, I was just going to go over the concepts first, so just we're all on the same page of that. I'm just going to kind of start from the beginning. This is the first time I really dug into it. So heat rate. BTUs coming in, and then the kilowatt hours going out. It's kind of like the opposite of an efficiency, isn't it? I mean, because the BTUs are coming in, the kilowatt hours are going out. Normally an efficiency would be the other way, but there it is, heat rate. So the lower the heat rate number, the better the performance. So it's the inverse of efficiency, as I just said. combustion turbines, the CT. Okay. Okay. How are you doing on question number one? Dustin, do you want to look at that a little bit, or are you good?
Yeah, I'm not sure how to get the water velocity.
Okay, so let's take a look at number one. Okay, so make sure your assignment 8.2 is correct using the key. The key has the exact cell formulas instead of the algorithms. Copy assignment 8.2 and rename it as 1. Now, does he provide 8.2? Can we just go and grab it? Or are we relying on our own, maybe correct, maybe not?
He gave us the key and resources. But I did it correctly last week for once.
Way to go, man.
Right, assignment 8 key.
Assignment 8 key, is that under resources 8? No, it's going to be under resources 9. Right?
Yeah, it's just under topic 9 now, it's not even in the resources.
Oh, there we go, assignment 8 key. Okay. Which one should I pull up, the JPEG or the final?
PDF.
Okay, PDF. Save file. VTC, Power Systems, Courses, VTC 214, 2015. New folder. Week. Modified. Open. Open. Save. Take a look at that bad boy.
Velocity, button friction head. So that's from the net divided by height area. Convert gallons per minute.
And what part of this pump storage do we need? Because I don't see, there's no formulas in the PDF.
Right, so this is just this is last week's version.
Let's see what you got.
That's what you have for him, right?
Yeah.
So this is last week's one, so it's good. Trying to keep friction that goes into it.
Okay.
Lots to see. Yeah, so basically throw that efficiency in the pump and
Do you have an Excel you can send me? Just, why don't you shoot me that, and I'll get started with that. I'm not sure I built that full Excel. I didn't build it fully anyway. Okay. You can get an Excel going last week. Oh, pump time rows, is it? God, I'm having the same issue with my Excel. It's not. I'll move that up. old one there, power factor. Whew. That's old, no problem. Are you sending me that guy?
Yep.
Yeah, so, okay, I'll start with that.
Okay.
Yeah, thanks. File, save as, courses, 2015. Nine. Thank you, Dustin. Okay, so is this, does this have additional stuff for week 9 in it?
Just the friction variables.
Right here, okay, pipe length, pipe radius, pi, gravity, pipe area, generation water velocity. Okay, great, thanks. File, save as, week 9. Okay, I'm just going to call it learning unit 9. Yes. Okay, so let's get into assignment. We're still on problem 1, right?
Mhm.
Okay. Just this problem account for friction. This will reduce the energy available to the generator and increase the energy requirement of the pump. The length of the pipe or penstock is 1,400 feet. Good. So we got length versus pressure. I think we were able to convert head to PSI last time. Friction head is related to the water velocity. Okay, so let's just look at that equation for a little bit. Head sub friction. Well, you can't see what I'm doing, but if you want to see what I'm doing, you just come over here. I'm recording this. So friction head equals the velocity squared. And I'm going to try to make, well, that's a little v, so no serifs on it. divided by 2G. Right, okay. Are we given gallons per minute?
Yeah, it's the same as last week, so it's 140,000 for the generation. So-
Okay, all right, so here's how we want to think about it. And what we're going to do, so we need to get velocity from flow rate. Is that basically all we're working on?
Yeah.
Okay. So that's fairly straightforward. So let's just draw a little picture. Again, most of these things come back to your through variable times your across variable. So what you've got in the pipe is velocity. Now, another thing to think of this, it's actually going to be the average velocity through the pipe, because you're going to have kind of a little velocity at the edges. You're going to have a bigger velocity in the middle, but overall you're going to have some, we can just call it V bar, the average velocity, and that's really what we're dealing with here is the average velocity. So you also have a flow rate, and we're just going to call that, for now, we'll just call it Q. Hopefully that's not, sometimes Q is also used for heat, but it's also used for volumetric flow rate. And then you've got an area. So a little bit of dimensional analysis will help us here. So we know that the dimensions of the volumetric flow rate, we're just going to put that as length cubed per unit time, right? Because it's going to be gallons per minute, cubic meters per second, what have you. So it's volume per unit time. Now we know that velocity has dimensions of length per unit time, and we know that area has dimensions of length squared. So if you look at these three things, here's your volumetric flow rate Q, here's your velocity V, and again, don't confuse V with volume. In this case, it just means velocity. And here's your area L. We should be able to see right away that Q equals AV. So, and again, just if you think about this just for a little bit, the bigger the pipe and the faster it's flowing, the bigger your volumetric flow rate. So from that, and what do we have? We've got Q and we need V.
Yep.
Yeah. So then we'll just change this around a little bit and just say that V equals, go back up here, Q over A. So let's throw some numbers in, and we want.
That's what I did. I just didn't look like the right number to me.
Okay, good. And now is the velocity in feet per second? It better be, right?
Right, it's supposed to be
Okay.
gallons per minute.
Okay, so the velocity we're going to need. And what's the value of Q? How many gallons per minute?
140,000.
140,000 gallons per minute. I probably wrote that too big, but that's okay. And then what we'll do is let's just get between gallons and cubic feet. And let's just say it's going to be better if let's just use a number bigger than 1. So let's look for gallons per cubic foot, 7.48. So there are 7.48 gallons in 1 cubic foot. And so far so good. Gallons are going to cancel. And then the problem is asking for feet per second. So we're going to do 1 minute is 60 seconds. And that's our Q, and then so what I'll do here is I'll just write Q in cubic feet per second is what we're looking for. So let's just do that math. And right now we're just converting Q. We're not going to worry about V just yet. Okay, so here's 140,000 divided by 7.48 divided by 60 equals 312. 312 cubic feet per second. And 140,000 gallons per minute is a lot. 312 cubic feet per second is a lot, so I'll believe that. Let me just go back and make sure our gallons cancel, our minutes cancel, and we're left with cubic feet per second. So there's our Q. Now let's go after V. V equals 312 feet cubed per second. And then we're going to divide that by our area. And the area is pi, well, it's pi times r squared. What's the radius? 2.5 feet? 2.5 feet. And we're going to square this whole thing. So what we can see is we go, take that 312 divided by pi divided by 2.5 divided by 2.5 equals, I'll call it 15.9 feet per second. Feet per second. All right, so now we've got a velocity. Let's see if anybody logged into the Blackboard or not. Okay, that's all right, it's just me. So 15.9 feet per second, there's our velocity. All right, so now we can go back in and calculate our fluid loss. Take this whole guy, copy, come back down here, let's go on a new page, paste. So HF equals, so we can throw in our 15.9 feet per second, and this whole guy is squared. And now we're looking at 2 times 32.2 feet per second squared. So here's our 15.88 times 15.9 divided by 2 divided by 32.2 equals 3.9. 3.9, and this is kind of strange dimensions, but it's going to be feet. This is feet of pressure. I think the way it's given, if we go back here, feet per 100 feet, if that makes sense.
Feet of pressure per 100 feet of length.
Yeah, so you're gonna lose 3.9 feet of pressure, and we can convert that to PSI per 100 feet of pipe. So 3.9 feet of pressure per 100 feet of pipe. So the way to think about this, let's just look. And how long is this pipe we're talking about? 4,500. Okay.
That's a long one.
That's a long pipe. All right. So, and again, you know, we've always in the past used water as an analogy for electricity, and now we can actually use electricity as an analogy for water. Because if you think about electrons flowing through a copper wire, you're losing some of that energy to heat. In this case, well, we're still losing it to heat, but we're losing it in the case of friction. So all that water is just churning around. So the whole pipe is 4,500 feet long, and you're going to have across the entire thing a delta P, a change in pressure. And well, if we just chop it up into 45 sections, you know, just keep chopping it up, we're going to lose 3.9, no, let's not write it down there, delta P equals 3.9 feet times 45, because there are 4,500-foot sections. So 3.9, let's go back to our calculator, times 45 equals, so we're losing, it's a lot of pressure, losing 177 PSI, or 177 feet. Equals 177 feet. Now if we come back here, PSI would become, it was 2.3 PSI per foot, right?
Or a foot per PSI. Yes, I-
1 foot. Oh, there we go. Yeah. 2.3 feet per PSI.
Mhm.
2.3 feet per PSI. So 177 divided by 2.3 equals 77. 77 PSI. Okay, that's a lot of calculations. I'm not sure where it's gotten us. But let me just review. Okay, so first we decided that you're losing, and again, these are kind of weird units, but H in feet, and H from last week, we know that is head of pressure, and that just goes back to one little 1-inch square column of water. A column of water that's 1 inch square and 2.3 feet tall is 1 PSI. We also know that the faster water flows through this pipe, the more pressure we're going to lose, and that's just from turbulence. And then the 2G is just our constant in this case. Did some dimensional analysis and converted volumetric flow rate to average velocity, knowing the area in the pipe. Converted gallons per minute to cubic feet per second. The reason going to cubic feet per second is that we could get to feet per second in our velocity. So we got back down here and calculated our velocity. 312 cubic feet per second divided by the area. I got 15.9 feet per second as our velocity. We could then plug that in to get our change in pressure per 100 feet. And we came back with 3.9 feet of loss, feet of head pressure per 100 feet. We know that the pipe is 4,500 feet long. So our 3.9 per 100 feet times 45 got us to 177 feet of pressure, which is 77 PSI.
I think we just need the feet of pressure, so subtract that from the average head then.
So we didn't even have to get to PSI? Okay.
So this, yeah,
So the 177 is good.
so you subtract that from the 900 feet of average head, I guess.
Oh, yeah, okay, good. So we didn't even have to go to PSI, but there we are with 177 feet of head. Okay. I'm going to save that. Drop that in the course here when I get back. All right, I'm going to call that a wrap on that particular session and get back into another one. That's 30 minutes there. All right, so hopefully the physics there made sense. Now we'll get back into Excel and see what we can do.